Hi, welcome back. Here we're looking at examples of the fundamental frequency of continuous time. We're still working with only continuous time sinusoids. And sinusoids include sine, cosine, and complex exponentials. Okay, so I've got 4 examples here. x1, x2, x3, x4. Using just sines and cosines, and then after we're done with those, we will look at the complex exponential. So for all of these examples, I want to answer the question, is the signal periodic? Okay. And then if so, what are the fundamental frequency and the fundamental period? Okay, that's the goal here. Let's look at example 1. For example 1, I'll write it out here. Example 1. First, you should know from high school math that sines and cosines, they're always periodic, right? Continuous sines and cosines, that is, they're always periodic. You should have graphed these and looked at the graphs so many times and see that it repeats. The key here, so in example 1, we just have a sine, right? And the key here is this number that's multiplying the independent variable t. Okay, so that number here is the fundamental frequency. That's just it. So if you have a sine wave that's multiplying the continuous time variable, then that multiplication constant is the fundamental frequency. So what does that mean about the period? The fundamental period is 2 pi divided by the fundamental frequency. So that's 10. Okay, and again, if we were using units, you could think of this, the fundamental frequency as radians per second, and then the fundamental period as seconds, but we leave off units. Okay, so that was pretty simple. Let's take what we just did there and see if we can get example 2. Again, I look at example 2 and I have a cosine of a continuous time variable t. And what is multiplying that continuous variable t? Well, in this case, it's 2 pi over 15. So I know right away that my fundamental frequency is 2 pi over 15 just by inspection. And then I can deduce the fundamental period is 2 pi over 2 pi over 15, which is 15. So I guess example 1, we forgot to answer the question. Is the signal periodic? Yes. A sine of a continuous time variable is always periodic. Cosine is always periodic of a continuous time, yes. So there are our answers for examples 1 and 2. Okay, now things get interesting in example 3. I have the same 2 examples added together now. So we know that the first component of this signal repeats every 10 units of time. And we know that the second component of that signal repeats every 15 units of time. So how many units of time does it take for the whole signal to repeat? Think about it. Well, the fundamental period here is not 10. and it's not 15. Yes, this first one repeats every 10. Yes, this second one repeats every 15. But when this guy is done repeating, when it's reached the end of its first cycle, after 10 units of time, the second one is not at the end of its cycle yet because it takes 15 units of time. Likewise, when this one's done after 15 units of time, this one is midway through its second cycle, and it's not ready to repeat. Do you see what's going on here? Let's try to formalize this. The first one repeats every 10 units of time, but also every 20 units of time, every 30 units of time, 40 units of time, and so on. The second component repeats every 15 units of time, 30 units of time, 45 units of time, and so on. So when do they all line up again and are ready to repeat together again? Well, that's 30 units and 60 units of time and 90 units of time. But the smallest positive number is 30. That's the least common multiple. The least common multiple of the two individual periods. So for example 3, we would say that the fundamental period is 30. Now, what did that entail? Well, let's say you were just given the problem 3. You'd have to inspect this one alone, the first component, and get the fundamental period as 10, and inspect this one alone and get the fundamental period as 15, then find the least common multiple as 30. Okay, so now, once we have that, we can get the fundamental frequency. So we're kind of going in a different way here than we did the first two examples. So this is 2 pi over 30, or pi over 15. So the answer to the question, is it periodic, is yes. It is periodic, right? If you can find the fundamental period and the fundamental frequency, then certainly it's periodic. This is interesting, though, because the frequency is pi over 15, but notice that in this signal, we don't have pi over 15. We have 2 pi over 15, so that's twice the fundamental frequency. And we have pi over 5, which is actually 3 pi over 15. So this is 3 times the fundamental frequency. So interestingly, we don't even have the fundamental frequency there in our signal. We've got twice and we've got 3 times. And in the period of 30 units of time, this first guy has gone 3 cycles, and this second guy has gone 2 cycles. And they're ready to repeat then together again. All right, let's look at example 4. So I've got the sum of 2 sinusoids again. So taken individually, the first one has a fundamental frequency. I'm not going to use omega 0 here because omega 0 would mean the fundamental frequency of the entire signal. But the first guy has a frequency of pi over 5, and that implies it has a period of 2 pi over pi over 5, okay, which again is 10. Now the second component has a frequency of 1/10, which means it has a period 2 pi over 1/10, or 20 pi. Okay, so the first guy repeats every 10 units of time, the second guy repeats every 2 pi units of time. When do they repeat together? Well, the first guy repeats every 10, 20, 30, 40 units of time, right? And the second guy repeats every 2 pi, 4 pi, 6 pi units of time. What is their least common multiple? Well, they don't have one. This is this is a nice integer number, 10, 20, 30, 40. This is irrational because of the pi. So they're never going to repeat together. There's no least common multiple there. So this is not periodic, believe it or not. You would think that the sum of two things that are periodic would have to be periodic itself, but it's not the case. The frequencies are not integer related. So you can plot this. Go ahead and plot it in your calculator or whatever plotting software, MatLab, Python, whatever, and check it out for yourself. It does not repeat. Okay, let's look at some more examples. How about example 5? Three e to the j pi over 5 t. Okay, so example 5. Is that periodic? Yes. We've already talked about a signal that's in that form. What is its frequency? Pi over 5. What is its period? 2 pi over pi over 5, or 10. And as we saw from Euler, if you don't, if you're not certain about that, we can rewrite this as cosine 3 times the cosine of pi over 5t plus j times the sine of pi over 5t. Right? And so look what we have here, though. We have a cosine pi over 5, and we have a sine of that same frequency. So yeah, we've got the cosine of a frequency plus the sine of that same frequency, so we know that that's got a frequency of pi over 5, and so it has a period of 10. How about this guy? Example 6. 2 e to the j pi over 5t plus 3 plus e to the j 2 pi over 15 t. This is yes. Example 6. Well, example 6, I've chosen these numbers to match example 3. See that? Now we can convert. Now they're not exactly the same signal, but as far as frequency and period go, they are the same. We can convert the first guy to sines and cosines. And we can convert the second guy to sines and cosines. The second guy would have a frequency of 2 pi over 15. The first guy would have a frequency of pi over 5. So then it becomes very similar to example 3. So the answer to this is yes. That is periodic. Do you remember what the period was? So remember that this guy, the first component has a frequency of pi over 5, which means it has a period of 10. And the second guy has a frequency of 2 pi over 15, which means it has a period of 15. So the period with the least common multiple then was 30. So the period of this thing is 30, and so that means its fundamental frequency is 2 pi over 30, or pi over 15. Okay, so I think you get the idea now. I'm going to just remind you that of a certain other type of signal. Let's say we have something like this. 4e to the 3 plus j t. And we want to know, is that periodic? Okay, well, remember that the real part of the exponent has to be 0 for the complex exponential to be periodic. So the real part here is 3, it's not 0. So this is actually one of those things that oscillates, and it gets larger as it oscillates. So that's not periodic. No. Okay, and let's look at another one, example 8. How about 4e to the negative 2t? Okay, think about that. Example 8. Example 8 is not periodic. This is a decaying exponential, so that certainly does not repeat.